So if you're like me and you had a chance to explore Toronto for a little bit yesterday, you might have met up with a friend at a bar that's nearby and played some darts. And let's say that you and your friend decide that you really want to play some darts together, but as it turns out that your friend has never played darts before. So this is their first time playing darts. So before they start playing, let me ask you this. Can you raise your hand if you think that the first time that your friend is playing darts, it will land at bullseye? Okay. Now, how about somewhere here? Raise your hand if you think that it's possible that your friend's first throw could land here. Awesome, thank you. And now a slightly different question. Raise your hand if you think that after a lot of practice, your friend could get to the bullseye. So for example, 100 throws or even more. Thanks. So just with this really quick example, I hope that it's quite obvious that it's very easy for us to represent and think about someone's initial performance when they're learning a new difficult task. It's also not hard for us to think about someone's final performance after some practice. But how do we think about this process in between? Do we have intuitions about how learning actually unfolds over time? So this will be the focus of my talk today. And before I start talking about how we think about learning, I want to spend a little bit of time to talk about how we think about learning itself. And we start our investigation in the domain of skill learning because over the past decades, research have shown that many activities in the domain of skill learning unfolds exponentially over time. So if you look at this coordinate right here, x-axis being the number of practices and y-axis being the sizes of errors, an exponential learning curve would look something like this, where a learner would make lots of progresses early on, but their performance would asymptote later. So think back to the opening example of someone playing darts for the first time. It might take them only a few tries to get their darts actually on the board, but it's going to take them a lot longer for their darts to be right at the bullseye. Now, on the other hand, there have also been lots of work looking at how people, both children and adults, think about learning, including how they evaluate and predict their performances at discrete time points during the learning process, how they estimate the time it might take for them to learn something new, and open-ended questions asking children what they think learning is. Inspired by all those work, we want to go a step further and look closer at how people think about the learning process. More specifically, we want to know whether people hold fine-grained representations of learning as a process that unfolds over time. And the answer to this question is actually not that obvious, as people could be representing learning in a number of different ways. And exploring this question is not only theoretically important for us, but it also have practical implications. So if you think about it, if a learner misrepresents their learning progress, this could impact their learning motivations and decisions during the learning process. And now you might be thinking, how hard could it be for someone to represent the shape of learning accurately? As it turns out, research in other domains have shown that reasoning about exponential functions is actually quite difficult, as people tend to linearize the shapes of exponential functions. So this could suggest that there's a general cognitive bias that could hinder people's ability to represent learning at this fine-grained level. So it's truly an open question for us whether we can represent learning and the learning process over time. So to test this question, we designed 2 experiments. In experiment 1, we get the ground truth of people's actual learning curves. And in experiment 2, we ask about how people think about learning. And we designed a game that can be used across both experiments called Lollitos. And the goals behind designing this game is really simple. So 1, we want a motor skill learning task that we can use to construct learning curves. So it can't be too easy that people get perfect at it right away, or too hard that people can't get better after some practice. And we also want this to be novel. That's why you see this silly combination of the archery board and some lollipops. And lastly, we want this to be a game that people can play online using their own keyboards. So participants across both experiments get introduced to the game in exactly the same way. They're told that the goal of the game is to shoot the lollipop to be as close to the bullseye as possible. And they will use the space key to stop the lollipop from moving sideways. And they're going to hold the enter key to shoot it forward. And the longer they hold the enter key, the further away the lollipop goes. And participants get to experience holding both the spacebar and the enter key without the target board being present, so that they understand the functionality of this game without having a direct learning experience. And another benefit of using this game is that it makes measuring performance over time really easy. So based on the lollipop landing positions, we can construct the Euclidean distance from the landing position to the center of the target board and construct the learning curve across many trials. So now just getting into experiment 1, where we get people's actual learning curves. So participants are asked to play 50 trials of this game. And now let's look at some data. So on the x-axis here is the number of trials, and on the y-axis, the distance to center. So 0 would be right at the center of the bullseye, and 600 would be somewhere way off the target board. And what I'm about to show you is the individual level and average level learning curves. So we fitted this data to both exponential and linear models, and I will show you the model performance right now. So here on the x-axis is the individual participant, and on the y-axis is a different score comparing the exponential and the linear models. So above 0 would mean that the linear model outperforms the exponential model in describing a participant's data, but below 0 would mean that the exponential model did a better job at describing the data. And straightforwardly from this plot, you can see that the exponential models outperform the linear model in describing participants' learning data. So we replicated this result in our game Lollytoss, something that has been shown over and over again, that skill learning unfolds exponentially over time. And now that we have this ground truth, we're going to move to experiment 2, where we look at how people think about learning. And instead of asking participants to predict all 50 trials, which could be a quite tenuous process, we asked participants to predict a selected number of trials that's evenly placed across 50 trials. So now I will show you experiment 2A, which is a trees prediction game. So just to remind you, participants get exactly the same instructions as participants in experiment 1, but here, instead of actually playing the game, they're asked to click on the board where they think a learner's lollipop would land. So with this, we're able to construct the predicted learning curves. So again, here, x-axis is the number of trials and y-axis is distance to center. And we can see here both the individual and aggregate level participants' predicted learning curves. And we fitted this data to both the exponential and linear models. And here's what our result looked like. So quite surprisingly, we found that exponential models outperform linear model in describing participants' predicted learning curve. And people predicted learning to unfold exponentially over time. And this is actually an astonishing result for us, given that we did not know whether people are able to hold fine-grained representations of learning at this level, let alone that they actually predicted quite accurately. So to make sure that this result doesn't come from any experimental artifact based on how we're asking the question, we designed experiment 2B, a probability estimation game. And the goal here is to design a game that can be as different as possible from experiment 2A, so that we can make sure what we're getting is actually participants' intuition. So in experiment 2B, we divided the game screen into 4 different regions outside of the target board: the black and white rings, the red and blue rings, and the bullseye. So for each prediction a participant make about a learner's lollipop toss, they actually have to make 4 probability estimations about how likely the lollipop would land in any one of those 4 regions. And this is just an example of a participant moving the slider bar. So from this, we actually constructed a weighted distance to center based on participants' probability estimations for all 4 regions and the average distance from that region to the center of the bullseye. I'm glossing over some of the details here, but happy to talk more about this part in the Q&A. With the weighted distance to center, we can again construct participants' predicted learning curve in experiment 2B. And this is what the individual and aggregate level predicted learning curve look like. And here again, we fit both exponential and linear models to our participants' predicted data. And this is what the data, the comparison look like between the two models? So surprisingly, we see here that, again, exponential models outperform linear model in describing participants' predicted learning curve. And even with this more abstract and more difficult task, we found that participants can predict learning as unfolding exponentially over time. So now just putting all the results back together in one slide, we show that in experiment 1, participants learned lollipop in a way that replicated previous results that skill learning unfold exponentially over time. And in experiment 2A, we show that participants can accurately predict the shape of learning as unfolding exponentially. And we further validated these results in experiment 2B using a completely different method. And we see this as converging evidence that shows that what we're getting here is actually something concrete about participants' representation of learning. And although not shown here, we've also replicated the sets of data in in-lab samples. And now that we know that participants can accurately represent the shape of learning, we wanted to know whether participants can accurately represent the specific parameters in the learning curve, including the starting points, the ending point, and the learning rate. And for this part of the analysis, I will be focusing on only experiment 1 and experiment 2A, since in experiment 2B, we do not have direct point estimates. So here, what you're saying is just the average learning curve from experiment 1. And now I'm just laying on top of it the average predicted learning curve from experiment 2A. And just right off the bat, you can see that there are some discrepancies between those two learning curves. More specifically, if you're looking at the starting points, you can see that people predicted learners to perform better initially than they actually are. And for a more direct visualization, you can see here that participants' actual performance in red is more spread out than the participants' predicted performance for this very first task. Interestingly, though, as you might have noticed here, participants are quite accurate at predicting the direction of errors. So they predict that people are more likely to overshoot rather than undershoot at their very first task. Now looking at the endpoint, participants also predicted that learners will be better than they actually are after 50 trials. And here you can just see really obviously with both the density plot and just the very clustered blue dots, the participants predict that learners will basically be at around the bullseye, whereas the actual learning data shows it's more spread out. And lastly, if we look at the learning rate, we find that people predict learning to progress slower than it is in reality, which if you just look at the two learning curves here, you can see that the actual learning curve is more steep than the predicted learning curve. So together, I've shown you that when compared to actual learning data, people predict better initial performance, and they also predict better ending performance. And they predict learners to learn slower than they actually are. And granted, some of these misestimations could come from task-specific features due to how people are understanding this task. We're still interested in some of the implications that this could have on actual learning experiences. So now I'm just going to give you two quick examples. So imagine someone who accurately predicted the starting point of a task, but they predicted a slower learning rate than the actual learning rate. This person might actually never start learning this task because they feel like they will just never be as good as they want. And what about someone who predicts their learning rate could be faster than the actual learning rate? So during the actual learning experience, this person could be discouraged by their actual performance versus their predicted performance, and then give up prematurely. Although I can list many more examples here, I really just want to highlight the importance of studying how people represent learning at this fine-grained level. So to sum up, I hope that I've shown you that skill learning unfolds exponentially over time, but more importantly, people are surprisingly good at representing the shape of learning. But we've also shown you that people sometimes misestimate the specific parameters. We see this research program as something that's really generative and opening up to lots of interesting and exciting new directions. So I'm just going to quickly go over a few. As I've alluded to before, we're looking into how misrepresentations and misestimations of the learning curve could affect learners' daily motivations and learning outcomes. We're also interested in how generalizable are people's accurate representation of learning across different domains and across different shapes of learning curves. And lastly, with my collaborator, Brendan Carrillo, we're interested in looking at the developmental root of this question. How do children come to understand their learning performance over time? So if after my talk, you feel so inclined to try to play some darts yourself, I'd encourage you to try out to see how accurate you are at predicting the learning curves, and you can come find me afterward. And with that, I want to thank my amazing undergrad RA for collecting all the in-lab data, and my collaborator Sam and advisor Julia for diving into this project with me, and all my lab members for all the discussions. And thank you all for listening.